This section deals with geometric probability. You probably have done probability before, and this will work very similarly to that. The probability you did before likely had you building fractions that all fit the same pattern. In the denominator, you had the total number of possible outcomes, and the numerator was the number of outcomes from whatever thing the problem was asking for or targeting. Here's a typical problem from Algebra 1 and before. You probably were asked something similar. What is the probability of rolling a 7 with 2 dice? To answer this, you needed to build a fraction. On the bottom of the fraction, we need the total number of possible outcomes, and there are 36 total possible results when you roll 2 dice. On the numerator, we need the number of times our target comes up. Our target is rolling a 7, and there are 6 ways to roll a 7 when you roll 2 dice. Simplify, you end up with a 1 in 6 chance that you roll a 7 with 2 dice. Hopefully you did something like that before. Another common probability question you probably saw before involved cards somehow. You might have been asked to find the probability of choosing a random card from a shuffled deck, assuming the jokers have been taken out. So you build a fraction again. The total is on the bottom, and there are 52 total cards. The target is in the numerator, and there are 13 hearts in a deck. Reduce that down, and you have a 1 in 4 chance of drawing a heart randomly from a shuffled deck. Now, since I have this animation here that shows a royal flush, I will sometimes have a student ask if I know what are the odds of drawing a royal flush, and I do. This is a calculation you probably haven't done before, but you will likely be able to do it after taking Algebra 2. It is still just building a fraction, though. There is almost a 1 in 650,000 chance of drawing a royal flush in 5 cards. The calculation is more complicated, but what you do in the end is still the same. You build a fraction, with the total number of possible outcomes in the denominator and the target in the top. In this section, we are going to be doing 2 types of geometric probability, but they work in just the same way as you have done before, and the examples I have shown up till now. For linear probability, we are dealing with lengths, but the total length goes on the bottom and the target length goes on the top of our fraction. With area probability, we are dealing with areas, but the total area goes in the bottom and the target area goes in the top of our fraction. They work just the same. We are just building the same kinds of fractions you have done before. Here is a more detailed look at what linear probability will look like. Here is a line segment, and we are choosing a point at random on line segment AD. The total number of places our point can land is the length of AD, so that goes on the bottom of our fraction. Our target is line segment BC, so the length of BC goes in the numerator. That's all there is to it. Here's what it would look like with actual numbers involved. Here my total is AD and my target is BD, so that's the fraction I build. It should be easy to just plug in numbers, but don't forget to simplify. Your final answer should be 8 over 13. Let your calculator simplify it for you if you need to. This is a more complicated problem simply because it's a word problem. And at first, you wouldn't think that this is a linear probability problem, but it is. Here I have a situation with a cable company. If you have ever dealt with getting cable set up in a home, this is the kind of situation you likely dealt with. They will often tell you a long stretch of time that you need to be at home, and they will, hopefully, show up sometime in that time frame. It's kind of ridiculous. In this case, you are asked to be at home from 8 a.m. to 3 p.m. But you have something come up and are not there for the first 15 minutes of that block of time. We want to know what is the probability that you miss the cable guy coming, assuming it is equally likely he shows up at any minute. So you might be asking, why is this a linear probability problem? Do you see any line segments here? Actually, we do want to build a line segment, specifically a timeline. We want to show a timeline with the hours from 8 a.m. to 3 p.m. That is our line segment. This timeline shows the total amount of time for our problem. But we were gone for the first 15 minutes, so this 15-minute block of time is our target. We are still just building fractions. So our fraction would look like this. Fill in our numbers, and we have 15 minutes over 7 hours. We want our numbers in the same units, so convert those hours to minutes and it looks much better. Finally, just simplify it down. There is a 1 in 28 chance that you miss the cable guy coming. Now, according to Murphy's Law, there's a 100% chance that you miss the cable guy. But amazingly, Murphy's Law never shows up in a math question. For those of you who don't know, Murphy's Law says if something bad can happen, it will, so you clearly were going to miss the cable guy no matter what. We also have an area probability, but it works just the same. Target area over the total area. Here I have 2 amorphous blob-like areas. It doesn't matter how you would calculate their areas, you just need the concept down. We are still building fractions with all of this. You put the area of the total in the denominator and the target area in the numerator. For example, a typical question will tell you a point is chosen at random somewhere in a shape. Here that point is chosen randomly somewhere in region R. And then you'll be asked what is the probability that it falls within some other shape inside of that bigger shape. Here this question asks that what is the probability that point also falls in region S. The point can fall anywhere inside of region R, anywhere in this blob here. That is what would go on the bottom of your fraction. Clearly we can't find the area of this blob, But in the problems you will be asked to do, there will be shapes that you can find the areas of, and they will use all of the area formulas you've used up till now. Areas of rectangles, rhombuses, trapezoids, and the rest. All of them are possible. Sound fun? Whatever the area is for your total number of places your point can fall ends up in the denominator. Our target area is region S. That area calculation would go in the numerator. That is all there is to geometric probability. You are simply building the same kinds of fractions that you have been doing with probability from before. Target over total.